simple. So for different amplitudes, with large angle scattered amplitudes, you have all the external momentum. They are pretty large, the level standard. But you also have an additional soft gluon, and which is parameterized by small parameter delta. And the question that I'd like to ask is, what does the amplitude behave in the limit that delta is very small? And I'm only interested in the leading term in this expansion, not the rest. And I'm interested in the loop level of these relations. So the outline of this talk is the following. I will first explain why we are interested in this limit, this approximation. And I will review the factorization that goes to all orders for how the amplitude behave in that limit. And then I will present a calculation of that universal factor that governs the soft limit go to two loops. And then I will talk a little bit about what that results imply for a violation of factorization at amplitude level. So there are many reasons why we study this limit, but QCD itself doesn't allow an infinite low energy gluon because it can cut off around the QCD. However, for very practical reason, for collider physics, for very practical reason, if your observer is well defined and infrared state, the observer shouldn't depend on the low energy dynamics. That means that if you choose your observer nicely, you can in fact integrate the gluon momentum to zero without causing any problem. But when you do it diagram by diagram, you run into problems. For example, when you do that integral for loop fractions, integrate from 0 to infinity, you get infrared divergences from the loop fractions. But it's well known that if you do the same integral for the real radiated fractions, you get the two pieces cancel. Infrared divergence cancel each other, so you get a final result, which means that the observer that you're interested in doesn't depend on the low energy number dynamics of QCD. So but in practical, that's for this part you know how to do the integral analytically. But for this part, sometimes you want the observer which is more differential. So say you want to know how many jets you have in the final state, or what's the PT of the heavy quark is in the final state. So you want to do this part numerically. When you want to do it numerically and when you work in dimensional representation, it runs into problem when you're very close to the soft gluon limit. The integral diverge in that limit. So you cannot do the numerical integral naively. So one way out is to use the soft gluon approximation. In that limit, you have to do that integral analytical in order to cancel the infrared divergences from the loop fractions. But doing phase-based integral analytical is not that easy. In particular, if you have very complicated integrand. But you can use the soft gluon approximation there to simplify your integrand such that you can carry out the analytic integration in that very small region of phase space that you want to carry out analytically. That's one reason, for very practical reason. The second reason is also a phenomenological one. When you actually look at actual observer that people are interested in about in hadron collider, for example, the PD distribution of Higgs boson, you see that actually the distribution itself exhibits a very large hierarchy. For example, the production of Higgs boson itself will happen at a scale which is much larger than lambda QCD. And it's also much larger than the PT of the Higgs boson. The PT of Higgs boson, in this case, carry out next to leading log with summation. The peak is around 10 GeV. It's much larger than lambda QCD, but it's also much smaller than the center of mass energy. So you have three hierarchy scales. So you can imagine that in this region, you can use soft approximation to do the calculation in this region. You don't need the full QCD. You just need an effective Lagrangian that only contains a soft gluon and also collinear gluon to actually get the peak correct. That's the other actual motivation. There are also some more theoretical motivation. For example, if you look at some jet observer at hadron collider, for example, this is an event of two dijet production. And the jet, if you have some mass, if you calculate the invariant mass of all the particles inside that jet under some algorithm, it's found there are some mass. And so the mass of that jet is an observer. You can calculate, you can measure, compare with experiment. But the problem is that this usually such observer will have large logs in it, so you want to resum it. And those large logs, the origin of those large logs are from soft radiation. In this case, there's a very notorious large logs, which you call non-global logs, which is originate from when you radiate a gluon outside the jet, which doesn't contribute to the mass. But then it radiates back into jet, into the cone, which contribute to the jet mass. And actually, there's a very well-known set of equations that govern how these large logs evolve, and which is called the BMS equations. So in order to calculate this equation to higher order, you need to know the soft gluon approximation to higher order or higher loops. There's another interesting thing about this equation. This equation, when you perform when you go do a conformal transformation, it looks exactly the same as the BFKL equation in packed parameter space. So it turns out that you can use soft. So you turn the story in this way from BMS to you get a BMS, you automatically get a BFKL. So you can just use soft gluon dynamics to get a BFKL. That's also a very interesting thing. And yeah. And also this is a conference for amplitudes, so I should also mention the motivation for amplitudes. So far, for amplitudes, there have been a lot of progress in the past few years, but still for 5 gluon scattering at 2-loop level, even in pure n-4 Sylvian theory is not known at integrated amplitude level. So it's for the full NC dependence. So it would be great to since we know the soft factorization pretty well. Actually, you can predict the 5 gluon scattering amplitudes with one of the gluon become very soft. And that could give you a track when you actually do a full 5-point calculation at 2 loops. And also, it's not entirely impossible that in the future, you can use those constraints, the collinear limit, as well as the soft limit, to do some kind of bootstrap of the full 5-point amplitudes. And this information, the information from soft limit is orthogonal to the collinear limit. It's it gives you different information. So let's return to the soft factorization. At 3 level, it's a well-known. So every quantum field theory course say a little bit about it. So if you have a scattering amplitude which have a bunch of hard particles, large angles, hard particles in it, and you also want to have an amplitude with one soft gluon in it. So the step is very simple. You insert a soft gluon into these diagrams. You only insert it into external line. Because if you insert a soft gluon to an internal off-shell line, you can just drop the soft gluon momentum in the denominator. So it doesn't give you a leading soft dependence. You are only interested in the leading term of the soft gluon momentum. So the only place that the soft gluon can be inserted is to an on-shell external line. And when you do that, in this case I show a Fermion case. You found that the Fermion, actually the result when you do that insertion, you found that the result is independent. It is completely independent of the helicity or of the external particles. So this exhibit some kind of universality of soft gluon insertion. It doesn't depend on the helicity of the particle that it's coupled to. The only thing that you care about is the direction and the color charge of that hard particles. And TA here is denotes that it's a non-abelian analog of electric charge. So that formula can summarize in this way. When you insert the soft gluon in every possible position of the external leg, you get a result in this way. You get a soft factor, a 3-level soft factor of this form. And this 3-level soft factor is pretty nice because you notice that it's actually independent of the actual, it's rescaling invariant for the hard momentum. So if you rescale the hard momentum by a non-zero number, the result is unchanged. The physical reason is very simple because you are emitting a soft gluon. It has a very long wavelength. But all the hard particles, because they are high energy, so they are very localized objects. So the long length wave doesn't probe at how much energy you actually have for those half particles. And you also notice from this expression that the soft factor itself is gauge invariant if you replace the polarization factor by Q. And a useful technique that would be, I should say a little bit about is that when you have soft gluon emission or virtual soft gluon exchange between given half particles, it's useful to thought of the couple between the soft particle and the half particle as a user line. The reason is that when you sum over all those soft gluon insertion into a half lines, this is each term that you can get from Feynman diagrams. And in the denominator, I have systematically elected a k-square term. K is the momentum of the soft gluon. I assume that k-square is much smaller than n dot k, so that I can elect that. So you found that this is exactly a user line in momentum space. So it's useful to represent a soft gluon coupled to a half particle using a user line. That's what this notation means. In a full amplitudes, with the soft gluon, you can factorize it as a half amplitudes without a soft gluon times a user line, which is emitted in gluon. There are several different ways to write a tree-level soft factor. So if you want to keep the full polarization factor dependency, it's in this form. But you can also use spin analytic formalism to write the results for a positive polarized gluon. That will have this form. You can also express it as a two-dimensional correlator on a complex plane. That can be done by, so you have some momentum in here. So you can, these momentum it only depends on the direction of the angle direction, doesn't on the magnitude, doesn't depend on the magnitude for the half particle. So you can, for the half particle, it can be represented as a coin on the two spheres. So you can use a spherographic projection to project this expression onto the complex plane. And that will turn out to be useful at loop level. So that's for tree level. Tree level soft approximation is well known many years ago. But with the significant advance in perturbation calculation, people began to study soft approximation at loop level. And the first one loop soft factor it's not calculated directly from Feynman diagram, but is extracted from a one loop 4 and 5 Harmonic amplitudes. So given that if people first calculate the full amplitudes and then they take the soft limit to extract the soft factor, that's how it actually works. You take the one amplitudes, take the soft limit, and you found that there is a thesis which is proportional to a one loop with one less particle amplitudes times the tree level soft factor, as well as a one loop soft factor times the tree level amplitudes. So in that way, they can extract the color strip soft factor. And also, these you can actually calculate that soft factor directly from a Feynman diagram, so some Feynman rules, and that was done in 2000. And you can generalize that proof to all easily using the vector physics. So let me briefly explain how that factorization works at one loop level. So the idea is that you identify all the relevant scaling of loop momentum that contribute that leading power. So there are, say, for example, you consider a virtual photon decay to two methods particles exchange a loop particle with momentum k. So you ask the question, what kinds of momentum scaling that has leading power contribution? So there are three types of contribution. First one is a half scaling, the exchange particle has half momentum. So you can have a collinear particle exchange or a soft particle exchange. Potentially, you can also have another scaling, which is traditionally called our gluon region, which has this type of momentum scaling. However, this type of scaling is actually not something we like, because when you have a scaling of this form, you found that the last component is the perp directions. So the perp direction of that gluon is actually the square of the perp direction of the global gluon is actually the same order as the plus direction of the minus component. So when you do you are no longer allowed to use the ideal approximation in your soft amplitudes, which means that you cannot drop the k squared in the denominator when you have global reset. However, the global, it's known that the global gluon only contribute to the imaginary part of the amplitudes. So suppose we are only working in the Euclidean region, we don't have any imaginary part, so you can forget that piece. We only get the full amplitudes in Gaussian space with the imaginary part by analytic continuations. So if we don't consider that part, then a general one loop amplitude can be writing three pieces. Now this is the amplitude without the soft gluon. But now we want to insert a soft gluon into that hard amplitudes. So we consider how different pieces behave. Suppose you insert a soft gluon into a hard amplitudes. So that's trivial. Because it's a hard amplitude, the loop momentum is highly offshore. So if you insert a soft gluon into a highly offshore momentum, it doesn't give you a 1/delta singularity. So you don't need to consider those diagrams. The only diagram that matters is the soft gluon is inserted into an external line. So that can be factorized immediately as a Wilson line. So that's so diagrammatically, so in equation you can write this as a tree-level soft factor times a one loop amplitudes without a soft gluon. Then you can consider the soft gluon insertion into a collinear diagrams. If you're working physical gauge, you see that the unsuppressed, the diagrams that are unsuppressed are those of the self-energy fractions form. So if the scaling of the loop momentum is collinear, then it must be a self-energy type fractions. And you insert a soft gluon to a self-energy loop. Now because all the loop particles are collinear to each other, so it's parallel to, for example, one external leg. So due to color coherence of QCD, inserting a soft gluon into different positions can actually factorize as a self-energy without soft gluon insertion times a tree level, times a Wilson lines. That's the soft collinear decoupling of QCD. So in this case, you also found that the amplitude factorized at the tree level soft factor times a one loop collinear soft amplitudes. Now you almost have the factorization form you want. If you have a hard factor, a amplitude with only hard gluon times a tree level soft factor and a collinear amplitude times a soft factor. So if you want to complete this sum as a full one loop amplitude without a soft gluon, you only need to add the amplitude with only soft gluon in the loops, and then you subtract that pieces in order to double count. So you found that the first line gives you exactly the tree level soft factor times one loop amplitude. But for the second piece, because every gluon is soft, so you can systematically use Heisenberg approximation for the loop soft momentum, or in this case or this case. That gives you also a factorized form. That also gives you in other words, we can replace the half particle by just Wilson lines. So you found that the second line you have a tree level amplitude times a soft gluon addition of Wilson lines. That gives you the definition of one loop soft factor. So this is how the factorization at one loop works. You can actually carry out the same argument, or you can use an effective field theory argument, you can see that at two loops, the amplitudes in the soft gluon limit should factorize in these forms. Some of these pieces are universal. For example, the soft factor should be universal. It doesn't care about the helicity of the hard particles. So the things that we are interested in is the universal two-loop pieces. The one loop is known, the tree level is also known. So we are interested in the two-loop soft factor, which tells you some information about two-loop amplitudes in soft limits. So they are not, for this particular universal factor, there are not many diagrams we need to calculate as such. At one loop is just one diagram, at tree level just one diagram, one loop is also just one diagram. At two loop you have a bit more diagrams, but it doesn't exceed the number that you can manage by simple computer code. So if you look at if you think about what kind of diagram you can have at two loops, the most complicated one looks like this form. You have three views of line and you immediately solve gluon with two loops. You can have at most three views of line. If you have more than three diagrams, simply vanish in dimensional regularization. So if you count how many nanoscale variables you can write down, there are quite a bit of them. You can have 6 nanoscale variables. But thanks to the scaling symmetry of the soft limit, which tells you that the result doesn't change under a scaling of Pi. So the actual independent variables that you can write down, the number of independent variables is just 2, written as the cross ratio of Sij. However, Sij is not a very nice variable. They are actually in Euclidean space. U and V, they are not very nice because they are constrained variable in Euclidean space. You can actually work out the exercise. You found that U and V satisfy an inequality, which tells you that the square root, this expression under the square root must be smaller than 0. So U and V are not free variables. So in last lecture we hear about that it's good to have free variables, but U and V are not. But it turns out that the very natural free variable that you can think of is the one that you get from zero graphic projections, which is given in this form. And also because of one symmetry, you have the SL2C symmetry on the complex plane, so you can actually fix three point on the complex plane to 0, 1, and in infinity you get a factorization for U and V, which is this form. The good thing of this factorization is that Z is a free variable now, so it's not a constrained variable. And also, because the amplitudes should be a continuous function of external momentum, so the soft factor should be single variable. Because for we shouldn't expect any discontinuity on the complex plane because they are just continuous evaluation of external momentum. And in particular, in the Euclidean space, we expect it to an analytical single variable function. So analytic single variable function on a complex plane is well known for the reason that it also appears in other contexts. For example, you can construct the single variable. So there's one class of famous single variable function, analytic function, or single variable harmonic polylogs that you can construct it just from the linear combination of the dimension of harmonic polylogs. The harmonic polylogs is just a generalization of the logs and polylogs that you encounter loop calculations. To show that it's actually single variable, you can make a plot of that host function to see that it's actually single variable. These functions, they occurred previously in many simulations. For example, multi-directionally 6-point major function, or in next talk we also hear about the appearance in the three-loop soft logs dimensions. So if you actually do the calculation, you find that at two-loop level, the sort factor can be written in two pieces. The first piece is the one that the sort factor only depends on two half directions, which is trivial. By scaling invariant, you know that this piece cannot have any canonical dependence on I and j. It must be just a single number. You can have a more complicated one, which depends on three half directions, three views and rounds. So the actual results look like this. If you look at the more complicated one, it has some color factor and some kinetical factor. The color factor is subleading in color, so if you work in large N series, you can never see those three-particle correlations. And for the kinetical dependence by both symmetry, we found that there are three terms, but it only depends on one function, one single function of a complex complex variable z. That function is expressed in terms of the single variable harmonic polylogs I showed you before. So these are some linear combination for single variable harmonic polylogs. The whole function, of course, is single variable since each individual piece is a single variable. And you see that there's a collinear singularity for this function, which is the P1 parallel to P3 or z equals 1. But it turns out that collinear singularity is cancelled between the two different pieces in the same term. So there's a collinear divergence in each piece, but there's also a collinear divergence in the second piece. They cancel each other. So the result, for this three-reason line contribution, we found that the result is free of collinear divergences in each of the collinear limits. That's for the result in the linear space, but for actual purpose, we want the results in cos space. So you want to do an analytic calculation. That could be a little bit. That's not that straightforward. You know how to do analytical calculation for Sij. Just by causality, you just add the IM superscription to Sij. But since our result is expressed in terms of complex variable z, which is a square root of u and v, so it's not that obvious how you should perform the analytic calculation with these set of variables. Also, the individual ingredient in our results contains all kinds of polylogs and logs, which have branch cap in z and z bar. So so you have to be careful how to perform the analytic calculations. So although it's not clear so for this expression, although it's not quite clear how you do the analytic calculation, but if you look at the derivative of this function, you found that the derivative of this function is very simple, just log u over c. So you immediately know how you should do the analytic calculation, just analytic calculate u, and you know how to analytic calculate u. That gives you the discontinuity of the derivative of that single variable harmonic polylogs. Once you know the discontinuity of the derivative of that function, you can integrate that discontinuity to get the discontinuity of that function itself. In this way, you can actually fix the discontinuity of that single variable function. Well, when you go back to Minkowski space, you see that the discontinuity of those individual pieces is no longer a single variable function. It has branch cap in the complex plane because you have the log z in it. But fortunately, when you consider the physical results, and simplify and consider every independent contribution. For example, we consider the color combination of this one